In the previous segment, we discussed about curvilinear motion, that is in 2D, the random arbitrary motion, and in that context we discussed about the NT coordinate system, the normal and tangential coordinate system, and before that we had also discussed about the Cartesian and the polar coordinate system. So, 3 coordinate system we talked about for 2D. Now, coming to 3D, that is the motion of a particle in the most general space of 3 dimension. There are 2 very specialized coordinate system generally which are used, and they are the cylindrical coordinate system and the spherical coordinate system, along with obviously the Cartesian coordinate system. So, let us start with motion in 3D, and first is our say Cartesian coordinate system. Now, this is the simplest one, and we all of us know and how they look like, but I am describing them so that the concepts which we will discuss here will be taken into the spherical and the cylindrical coordinate system. Okay. So, that is why I am just trying to draw it here. Say this is say x axis and say this is the y axis and this is z. Now, in any such coordinate system, we and then as discussed, so the position vector r will be obviously defined as xt I plus y t j plus z t k, where the k's I j k's are the unit vectors in say this is I, this is j and this being k. Okay, the unit vectors in those 3 directions. But then and then we know how to get the velocity, the velocity will be x dot I plus y dot j plus z dot k. So, these the explicit dependence on time I have not written here, okay, just for making it simple, and acceleration is just like that, x double dot I plus y double dot j plus z double dot k. Now, so they are very simply you can evaluate because I, j, k are fixed in space, and when you take the differentiation with respect to time, that differentiation does not come into picture, because you know what I mean, because this is a product, but it is a constant, so you do not have to differentiate it anymore. But then one concept which I want to make here is that of level surfaces. That means what are the level surfaces in the Cartesian coordinate plane. So, like what they mean is, if I keep say x fixed, the x coordinate fixed, and I change only y and z, then what surface do I get? Okay. So, that means in this case, suppose I choose x to be constant, so the surfaces which I will get are something like this, planes which are perpendicular to the y axis, say at this point it is passing through the x axis. So, x value is same on this full plane, and if I go that side, maybe something like that will be there, and we will get planes which are parallel to these planes. And now, so these are the values where so these are x is equal to constant surfaces. Similarly, if I would like to plot say y equal to constant surfaces, they will look something like this. Okay, and Similarly, I can put one more surface here. So like that. So these are y is equal to constant surfaces. So one coordinate is constant over that, and the other two vary over that surface throughout their ranges. And similarly, z, if I want to plot, it will look something like, say, this. Okay. So yeah, this is one surface, maybe another surface will look like this. Okay. So these are z is equal to constant. Okay. Now, so these why I have drawn them is, here they are very simple and easy to visualize, and that concept should be taken into the other coordinate systems when we deal with them. Okay. So this should be kept clearly in mind, and now we will move into, say, the cylindrical coordinate system, and then we will realize why understanding the level surfaces are so important in understanding the other coordinate system. Now, once we go to, say, the cylindrical coordinate system, that is coordinate system, in this what is done is, first we choose some arbitrary x, y and z direction. Okay. And now a point in space is now defined in three parameters, r, theta and z. Now, how, suppose you pick a point here which is P, then how it is done is like this. You join the position vector like that, and then you take its projection on the xy plane, say something like this. Okay. And then you look at this vector. Okay. And this direction will give you the direction of ER. Okay. And then this angle, say I'll put, say, this angle from the x-axis, whichever you have chosen, it's arbitrarily chosen. This is theta. Okay. So r, so this distance is r, and then the direction, the unit vector in that direction is ER. So this is r, this distance basically. And then if you just take the projection in this direction, so how do I take it? Yeah, so like that, if I take, so this height is the z coordinate. So the point P will be denoted by r, theta and z coordinate. So having said that, we can represent this vector or the position of that point to be, you know, say r is equal to r E r plus, say, z k. So like that we can actually represent. Okay. Now why we can do that is, you see, you can consider like this. Suppose this is, how should I do that? Okay, better way is, let me take this as, say, capital R. Let me do this. Otherwise it will be confusing. So what I'll do, I'll make it, say, R vector, so that this is your R, okay, and this will be R E R. Otherwise it will be confusing. Fine. You see this R E R is this vector, which you are adding with this vector, which is nothing but zk, and so this is the vector addition of those two. So that is how you will represent this one. Okay. And another way of looking at this is, and that will give you an idea that for representing some curve in polar or cylindrical coordinate doesn't mean that the particle has to move on a cylinder. This is very important. Always students get confused about this. They always think that cylindrical coordinate means a particle is moving on a cylinder. Not necessary. See, the thing is, this particle here now actually may be moving on some random path. Let me draw that, say here, something like that, and in fact its projection, if you see on the xy plane, will be maybe something like this. So here it will be something like that. So these are its projection. So whatever we discussed about a 2D plane, the curvilinear motion, and used our polar coordinate, the same thing happens on this curve basically. The RER is that coordinate which we define, and similarly E theta will be defined here in this direction. Okay. So E theta will be from here, E theta, okay, and Z direction is this. So exactly the same thing which we did for curvilinear motion of 2D will be done for this projected curve on the xy plane, and the extra information, which is the Z coordinate, is just being added here. Okay. So this is the 2D curvilinear motion, okay, on the xy plane, and that is what you are just adding up. Okay. And then the acceleration and velocity. So velocity will just be, you know, the differentiation of this thing, and we have done that in the polar coordinate part. I will just write it here, r dot er. So this is r dot er plus r theta dot. Okay. So now k is fixed in space with respect to time, but er is changing as soon as the particle is moving across this path, which is a 3D curve now. Okay. So, but this is a 2D curve which is living on this xy plane, and just while differentiating er, again you have to take into account that this varies with time. So from there it will come like, you know, E theta hat plus say Z dot k, right. So this is what will be the velocity. And if you write acceleration, it's exactly the same way we did for the other part. So it will be r double dot minus r theta dot square. It is in ER direction. Then two terms like r theta double dot plus 2 r dot theta dot times E theta hat plus Z double dot k. Okay, is that fine? Yeah. So these are the position vector, velocity vector, and acceleration vector which you should use if you are using the cylindrical coordinate to represent a motion in 3D. So this is a completely 3D path. Please try to see that. So I'll just use a so just to say that these are all, you know, projections, because we have already used the curve completely. So I can just, okay, So that is how the projections onto this plane. Okay. And that's fine. Yeah. Then we can go up to now the third coordinate system, which is the third one, which is the spherical coordinate system. Which is say r, theta and phi. Okay, I'll write it in this one, say r, theta and z. Have I shown all the things? So, okay, let me see er, e theta, and this is say k. So, these are our unit vectors, right. So, to this er, to this e theta and to this k. So, similarly for x, y, z also I should write this is x, y and z. So, I, j and k are the unit vectors. Similarly in cylindrical er, e theta, k, and here we will have er, e theta and e phi, the coordinate, the basis vectors, the unit vectors. Now, how do the coordinate system look like? Acha, before that I should in fact talk about the level surfaces of cylindrical coordinate, right? Now, in this picture it will be too complex. So, what I do, I'll just add one more page over here, and then in that I'll draw, and then I'll go to the, okay. Now, the level surfaces, if I want to draw, so this are our x, y, z. Now, r is equal to constant. So, that means if you keep the radius constant and you vary both theta and z, so you will get, you know, cylinders whose radius are the r value. Okay, that means cylinders like that. Okay, so like that. Similarly, okay, so like that. I shouldn't draw anymore. Anyways, that's fine. You understand what I mean. So, these are the cylinders which are of constant radius. So, if you are sitting on a particular cylinder, the radius value is constant, and once you move on them, the theta value changes, and if you move up down, the z value changes. And then what about say theta is equal to constant? So, they are planes at different angles. Say if I choose a surface at say at this angle, which is like that, and another say I'll choose at this, so like that. So, these are at different angles, you know. So, these are theta values. So, this is theta 1, so the other one will be at theta 2, so the third one will be at theta 3. So, if you move on these planes, so you will be keeping the theta value constant, and r you can change and z you can change. Okay, and then z is equal to constant surfaces will look something very similar to the Cartesian ones. Sorry, it should be say in this way, and yeah, so like that. So, these kind of surfaces will give you this parallel to xy plane. So, these are planes which will just cut these things, you know. These cylinders also will be cut at different locations like that, and so that will give you, and in fact if you see these curves, on them two values will be fixed and only one value will be changed. Because for example, on this curve, z is fixed, z is equal to constant, and on this r is constant, right? So this is r constant, z constant. That means if I move on such a curve which is actually the intersection of these two, so on this curve both r and z will be constant. So that means whatever changes is just the value theta. So that is why it's a circle. So these are called the coordinate lines, you can say, and then you get different curves like that. Similarly, you can go for say keeping theta and say r constant. That means these are this is say theta equal to constant, right? So if this is theta equal to constant and say this is r is constant, so the curve will maybe like something like this. Say this theta. Okay, so here somewhere if I join, so this curve, this is a line where both theta and r are constant. So then here both theta and r, they are constant, equal to constant. So only z is changing on that line. So that is how you should visualize that when you are using a particular coordinate system, then what are the level surfaces and what are the lines or the curves on which these level surfaces intersect with each other. And similarly, you can go for this is theta r, that is rz, and what remains z and theta. Yeah, so theta and z can intersect at particular things where in fact only r will change. Okay. Now we can go to say spherical coordinate system, in which again we will look for the xy coordinates like that, directions, because with respect to this the thetas and phis will be measured. So some x, y, z, and then if you now pick a point P here, then so then let's define, so suppose there is a point P here, then we will define the unit vectors. Let me change this points to somewhere else, maybe here. Yeah, then the unit vector in this same direction will be ER. Okay, and then and then the angle which this makes with say what do I call, say if I draw a perpendicular, so let me use some other color. Yeah, say if I draw a perpendicular, so then this angle okay, now this angle is theta. Okay, and now the angle which this arrow makes with this is say phi. Okay, now that's how you can define see either this or this angle, anything can be taken. There are two conventions, either you can use this as phi or this as phi, it does not matter. Say let's or let's say we will use some other color here, so this being phi. sorry, phi. You are able to see these three angles, sorry, two angles. One is on the xy plane, okay. This angle theta is on the xy plane, and then these points, say, let me call them, say, O, Q and P. So now OPQ constitute a plane which is perpendicular to xy and passing through Z. Now on that plane, let me, so on that plane this angle phi is measured, okay. So that is how, so using these three angles, I mean parameters, so this is R, so I will write, say, this is R, RER, and then theta and phi. So with these three parameters we will define that point's location. Now if you think about the level surfaces again, to exactly understand what these things mean, now constant R surfaces, you know, they are spheres, okay. Let me draw that here and I will come back there, because this picture is going to be clumsy if I draw there. Say, so suppose this is a big sphere, and let me draw some circles like that, so something like that, and now, okay, something like this, and then suppose I cut it, you know, from here, let's say from the center I am cutting it, then at different radius, so let me draw another sphere which is at this radius, another, say, at this radius, another, say, is at this radius, so like that. In fact, I should have drawn like that also, and yeah, maybe like that. So these are at different radius values, so these are level surfaces at different radius values. And then if I say, suppose I come to a point like this, say here. Now this is the R value, and if I go to this xy plane, so now this angle is theta and this angle is phi. So that means these circles which are drawn horizontally, okay, like the equator and the other latitudes on earth, okay. So they basically represent this angle phi, right. So constant phi lines are these circles. In fact, constant phi will be surfaces, so these are cones, you know, on that R will change and theta will change. So if you think about them, so they are you know, so like a cone here, if I take a cone like this, so that cone will be the surface of the cone, on that R and theta will change, but phi will remain constant. So those are different conical surfaces. So if I draw it here, so different cones, you know. So this is one phi. Suppose I go for another phi, it will look something like that. Say another phi if I go for then it will look something, say something like that. Okay. So these are different phi, and then on them the r and thetas are changing. Okay. And now these, so these are, I'll say what, phi is equal to constant surfaces. Okay. And theta equal to constant surfaces are, these are just planes like this. Suppose I draw a plane like that. So that is a plane, and different angles if I draw. So that's another plane, maybe that's another plane, so like that. So these are the planes, vertical planes, which are cutting all those cones and spheres. So these are like theta equal to constant lines, and these spheres are, spherical surfaces are r is equal to constant surfaces, and their intersections will give you curves on which two of those coordinates are fixed. Okay. For example, if I choose, say this theta equal to constant and this phi equal to constant, then I'll get some line like this, maybe here, okay, on this line. On that theta and phi both are constant, only radius will change. Okay. So and then if I go for, say r constant and phi constant, then I'll get the so phi constant, no? So yeah, phi constant means so we will get a longitude in that case. So phi constant, no, theta constant. Theta constant is a line, a plane perpendicular to the xy surface, and r constant is a surface. So these lines, if I draw here, suppose this line here can be called like, on that both r and theta, so they are constant. So only phi changes, and on, say, these kind of lines, maybe here, these kind of lines, which are the latitudes, on them are constant, and these are, cones are so phi constant. So like that you should think about the level surfaces on which two of them are constant, so that you can see that on that line only the other thing will vary, that is the theta will vary in this case, the phi will vary on this case, and on this r will vary. So this is how you should visualize the coordinate systems, and once we do that, and then here you can represent, the r vector, the r vector as say r times er, and from, we are not deriving them, the velocity will come something like, v r e r plus v theta e theta plus v phi e phi. Okay. And similarly acceleration, and in fact the acceleration terms are quite involved, and I'll just write them down. We will not derive them. You can refer to the book if you want them. So yeah, and here VR will be r dot, or yeah, so basically this I should make as capital R. Okay, this is a vector, and yeah, so r dot, and this is going to be r theta dot cosine of phi, and then this v phi will be r phi dot. Okay. So, this is how you will get the velocity, and the acceleration terms you will get as they are very involved terms, r double dot minus r phi dot squared minus r theta dot squared cos squared phi. This is the ER part. Similarly, the E theta part will be something like cosine of phi divided by r, then d by dt of which you can again differentiate, r square theta dot minus 2 r theta dot phi dot, okay, theta dot phi dot sine of phi. Okay. So, now this is with E theta plus 1 over r d by dt of r square phi dot plus r theta dot squared sine phi cosine phi. So, now this times E phi. So, that will be the expression for the acceleration. So, okay. So, these are quite involved expressions because everything changes, because see if you change one value also, r value, then theta also is getting changed and phi also is getting changed. So, that is why in every term all other things are getting involved. So, yeah, and then that should be fine to be able to use the spherical coordinate in any case. Again, I am repeating that there is no need to think that to use spherical coordinate the particle must be moving on a sphere. It is not necessary. It is just a coordinate system which you can use to describe the motion of a particle which is moving on arbitrary 3-dimensional curved path. Okay. So, just as a recap, we have seen today Cartesian coordinate and their position vector, velocity, acceleration and the level surfaces, and then the cylindrical coordinate and their corresponding expressions plus their level surfaces, and then the spherical coordinate and their corresponding expressions and its level surfaces. So, that is what was to be discussed under this coordinate system of cylindrical and the spherical coordinate system and the Cartesian also. And in the next segment we will discuss about the NT coordinate system and how it is used to describe general motion in 3-dimensional space, like we did for 2-dimensional space. See you in the next segment.